Okay, good morning, everybody. So let's get started. So what we are going to discuss here is site-specific ground motions for seismic design of LNG tanks. So now a structure, any structure, including LNG tanks, requires ground motions for design, for seismic design. So many disciplines are involved, in generating those ground motions. First of all, it is the geologists who tell us the time, location, and size of future earthquakes. And then the seismologists, they tell us how the rock will shake during these future earthquakes. And then we have geotechnical engineers who make adjustments for the soil. So they basically calculate the response of the soil deposit to the motion of the rock to generate the free surface motions. And then the structural engineers, they calculate the response of the tank to those free surface motions. So you see that many disciplines are involved here. So in the US, the United States Geological Survey, they do the work of geologists and seismologists. And as you can imagine, this work is very empirical and there are a lot of judgments involved in this work. So that's why I recommend that engineers should not try to duplicate this work. They should trust the work done by a federal authority like the USGS. And now in other places in Canada, Australia, New Zealand, we have similar authorities, who do this work. And then the engineers should focus on making adjustments for the soil and then calculating the response of the structure to those ground motions. So basically here what I'm saying is that the USGS that do the work of the geologists and seismologists, and then engineers make some other adjustments to generate ground motions for the design of LNG tanks. So we will discuss those adjustments in this seminar, in this presentation. So now API 625, ACI 376, or NFPA 59A, they require ground motions for dual level design of LNG tanks. So we are basically talking inner tanks, and then there is another ground motion required for the outer tanks. So they require two kinds of ground motions. The OBE ground motions, which have a return period of 475 years. So the purpose is, the objective is that during OBE ground motion, the tank should remain operational. During and after OBE event, the tank should remain operational. And then during and after the SSE event, the tank should not leak. It should hold its contents. So naturally, the OBE event is more common. I mean, and SSE event is rare. Right? So OBE event is 475 years. I mean, it's pretty rare also, but the SSE event is even rarer. Less likely. So according to the latest standard, so that is also the MCE event as per ASCE 7, MCER. So subscript R is basically risk targeted. So we will see how to generate the SSE ground motions, and then the similar steps can be used to generate the OBE ground motions. So we take an example site in Puerto Rico. So then you go to the USGS website and they provide us the hazard curves for this site. And for any other site, so just enter the latitude and longitude. So they provide you the ground motion parameters in the form of hazard curves. So basically these hazard curves, they say that anything is possible in the future, but higher values have longer return periods and lower values have shorter return periods, but anything is possible, right? So from these hazard curves, you read the 475-year return period ground motion parameters and the 2500-year return period ground motion parameters. So 475-year ground motion parameters will be used to generate the OBE ground motion, and the 2475-year return period parameters are used to generate the SSE ground motions, right? So remember, these are for rock. That is the work of the geologist, geologists and seismologists, they provide you the ground motions for rock. And the geotechs, they make adjustments for the soil. So these are the parameters for 475 and 2475 year return period at 0 second period, which is same as peak ground acceleration, and 0.2 second period and 1 second period. So we can plot them. They are shown here. And they are shown in the form of a response spectrum. So these red dots are the 3 values provided by the USGS. And like I said, if you are outside the country, then you will use the values provided by other authoritative agencies, who are supposed to do the work of the geologists and seismologists, right? And then we use ground motion prediction models to generate a smooth spectrum passing through these 3 values provided by the USGS. So these are the 2500 year mean return period uniform hazard response spectrum. So meaning that all 3 values, and all the values on this response spectrum, they have the same probability of being exceedance. That is why it is called a uniform hazard response spectrum. And remember that this is only for rock. We have not done the work of the geotechnical engineer yet. But the other thing we have to do here is that the seismologists, for some reason, they provide us the average of the ground motions in 2 directions. But engineers, we need the resultant, right? So when we are designing a structure, we need the resultant. What is the maximum it can experience in any direction? But the geologist and the seismologist, well, actually, I should say seismologists, they provide us the average, actually the geometric average. Let's say this is the motion in the east direction, this is the north. So they take the peak value in the east direction, peak value in the north direction, multiply those and take a square root of that. So this is what they provide. I don't know why they still should do that, but they continue to provide us the average while we as engineers need the resultant. So that is the first adjustment we have to make. So we multiply that by this ratio between the resultant or the maximum and the geometric mean. So when we multiply that, then we get a response spectrum in the maximum horizontal direction. So this is the 2500 year return period, maximum horizontal uniform hazard response spectrum, still for rock-like conditions. So then we apply these risk coefficients. These are specified in the code and they are described in the reference I provide at the end. So these are the risk coefficients. You have to adjust these ground motions, slightly reduced in most cases, but the factors are pretty close to 1. But still, to meet the code requirements, you have to multiply by these factors. So when we apply the risk coefficients, now we have an MCER response spectrum, maximum considered earthquake risk targeted response spectrum of rock outcrop motion, right? And it is always a good practice to plot the spectrum in a tripartite format, So here the acceleration is shown along this axis, deformation is shown along this axis, and pseudo velocity is shown on the vertical axis. But as engineers, we need acceleration and deformation. That is what we are focused on. We don't care much about the pseudo velocity, but it is a good practice to plot the spectrum in a tripartite format. Then it tells you if it has a reasonable shape. Many times I review these projects and I see spectra which really don't make sense. So you have to always plot it in a tripartite format. And then what you see is that it is missing what is called a displacement sensitive region. It has an acceleration sensitive region and a velocity sensitive region, but it is completely missing a displacement sensitive region. So you have to add that. So once you add that, now we have a complete response spectrum, but it is still for rock-like conditions. So we know the PGA is 0.447 G, that is a maximum acceleration, and this is the maximum displacement. Then the next step is, now we have to do the work of the geotechnical engineer, meaning that we have to bring it to the surface. This is for rock-like conditions. We need to bring it to the surface because that is where the tank is sitting, on the surface. So first thing we do is we generate spectrum compatible ground motions. So this is one of the 5 spectrum compatible ground motions that is generated. So this is the acceleration history, this is the velocity history, this is the displacement history. You should always plot all three histories. Acceleration history tells you about the high frequencies, displacement history tells you about the low frequencies, and the velocity history tells you about the intermediate frequencies. So this history is compatible with this response spectrum. So now we apply this history, ground motion history, at the base of a soil profile to generate the ground motion on the free surface. So again, we plot the acceleration, velocity, and displacement. You see the high frequencies are amplified in this case, but the low frequencies are slightly de-amplified. So now you have these histories, many such histories, 5 ground motion histories on the free surface you use to generate response spectra on the free surface for various values of damping. So you have to provide the structural engineers with response spectra for various values of damping. So once the structural engineer has this, now he has accelerations for various values of damping, the deformations for various values of damping. See, it is the job of the structural engineer to assign a period to the structure and to calculate its damping. So now the engineer has everything he needs to design his structure. So this is the MCER ground motion, which is also safe shutdown earthquake, SSE, or sometimes called CLE, contingency level earthquake ground motion for that particular site. So this is the response spectrum in the acceleration in the tripartite format, but you can also plot it in the acceleration format, acceleration versus period. So this will be helpful in linear analysis of tanks, right? So for linear systems, the period is well defined. So you calculate the period, and corresponding to the period and damping, you calculate the lateral force coefficient, right? And that will tell you how strong the tank has to be, right? But for nonlinear analysis, this is not helpful, because for nonlinear analysis, the period is not defined, right? Period only exists for linear system. So now you have to plot the spectrum in an acceleration deformation format, right? So here you read the force coefficient corresponding to the deformability, how much the tank can deform, and the deformability can come due to yielding, due to sliding, due to uplifting. So there are many sources of deformability, and also due to the interaction of the tank with the soil below, which is called soil structure interaction. So that provides you additional sources of deformability and damping. So you read the based on the deformability and damping, you read the force coefficient. So this kind of plot you will use for SSE analysis, for contingency level earthquake analysis. But this analysis, this spectrum you will use for OBE analysis, because you have to keep the tank operational during OBE ground motions. So, so basically what we discussed here is that the probabilistic seismic hazard analysis is highly uncertain and subjective. So that is why I say don't use any black box computer programs to just generate some numbers. You have to trust and rely on the work done by federal agencies like the USGS or the Canadian Geological Survey or the New Zealand Seismological Society, or whatever the agencies are in different parts of the world. So engineers should not question or repeat the PSHA by the USGS or other federal agencies. Engineers should make following adjustments for soil, and to convert the ground motion from average to max, and then from uniform hazard response spectrum to risk targeted, and adding displacement sensitive region, and generating spectra for various damping. So that is what the engineers, geotech and structural, should focus on. Engineers can also generate spectrum compatible ground motions from dynamic analysis. Sometimes engineers want to perform dynamic analysis instead of static analysis. So then they can generate spectrum compatible ground motions. So basically, so this is an upcoming book which explains all these steps in greater details. This is a publication of ASCE